So often we find ourselves in a situation where we need to solve an equation, an algebraic equation, that doesn't have an analytical solution. One example is given here. X squared over 4 minus sine of x is equal to 0. We can't directly solve this in a single step the way we normally would like to with algebra. Here's a plot of this function here. If we were to take a look at this, we could see very quickly that there's a solution here near 0 and a solution over here near 2. But we have no way to come up with what those actual numbers are analytically. So let's take a deeper look at this function. This is the intersection of two functions, x squared over 4 and sine of x. If we plot those two, then of course the difference between those two functions becomes 0 at the place where these two things are roots. So this is one of the really good applications of this skill, what we're going to be covering here, root finding, is to find a place where two equations are equal. This is good for optimization. This is good for solving vector loop closure equations in the case of a kinematic mechanism. A number of different applications for this, but we can reduce a lot of problems to a root finding problem, and the Newton-Raphson method is one of the more common methods to solve such a problem. So again, we have this trivial solution at 0. We can see by inspection, obviously, x squared over 4 is 0 at 0, and sine of x is 0 at 0. But what's more interesting is this intersection close to x equals 2. I want to know what that number is, and I want good values. I want accurate and precise values for x, such that when I plug it in, I get something very close to 0 for my function here. So one way to do this is graphically. Just take a graph and zoom in on it and do it again and again and again until your graph range and your graph domain are so small that you have a very good idea of where 0 is. We do this all the time. It's not necessarily efficient. It's not a great way to do it, but we do this on our graphic calculators, of course. What we want is something a little bit more optimized, though. We want to automate this process. So there's also the possibility of using a Taylor series. I could expand a Taylor series on sine of x starting from 0 and essentially add polynomial terms until I get an accurate assessment of what sine of x is this far away from 0, and then I would have a series of polynomials that I could then ostensibly solve analytically for the 0 that way. That's not all that efficient. It's not all that accurate. The number of terms I would need to use to get an accurate assessment of sine of x this far away from 0, and in this particular case we're not that far away, is pretty high. I mean, here we're looking at probably 12 to 15 terms in the Taylor series to get a good approximation for sine of x. It's not really great practice for this particular type of problem because it's going to vary from one problem to the next. We may or may not even be able to do that, but that is one application of a Taylor series that's valid, and it's one way to solve this problem. So what we're going to use is a numerical method, a way to approximate what the root is, take an initial guess, and then we're going to refine that guess using an algorithm and repeat and repeat and repeat. We do this because we have computers that are really, really good at repeating menial tasks very, very quickly. So that's what we're going to do with what's called the Newton-Raphson method. This is a method developed by Isaac Newton and some other. So the numerical method that was developed is essentially thus. I'm going to take a guess, and we're going to call that guess P1. And so my first point, P, is going to be here, P1. And I'm going to take that guess, and I'm going to say, okay, I'm guessing that the 0 is here at 3. And I'm taking a guess it's a little bit far from the 0 just purposefully, just so that we can see what the method is doing. But I'm going to take my guess here at 3. And what is the actual function value there? Recall that what we're trying to do is find where this function goes to 0. So we see, okay, well, the function value at 3 is just a little bit higher than 2. And so the Newton-Raphson method says, well, I'm going to take the tangent line to the curve at that point. I'm going to take the derivative, and I'm going to divide the function value by the derivative value at that point, and then subtract that from my guess. That gives me the intersection of the tangent line with the x-axis. And it does this repeatedly. And so I'm going to take that tangent line, draw it, come down here, and then this is my next guess. So this is guess 2. And so guess 2 I'm going to take up to the curve here, and I'm going to repeat the process again and again. And we can see that for most functions, well, we can't see that here, but for most functions that are differentiable where we can get easy access to the derivative and it's not too steep, etc., we get pretty good convergence, and it'll go very quickly to a root for the equation, assuming that there is one. So each time we draw that tangent line, we get a closer and closer approximation, and then we just stop our loop at some point when our guess is quote-unquote close enough. With a numerical method, we will never get the exact analytical result. We can get, however, very, very close very quickly. So let's take a look at this. Let's run through a couple of iterations by hand. And so just to reiterate, each new guess, for example, P2, would be equal to P1 minus the function divided by its derivative at P1. So let's say in this test case, again, that our function is x squared over 4 minus sine of x. And I want to find out where that's 0. And so I'm going to take the derivative. The derivative of that is x over 2 minus cosine of x. And so if I say for a moment that my first guess is 3, I can plug 3 into this equation, and we get this down here. So we get this kind of hot mess here, and we wind up with 2.153. And so just above 2 is our second guess, which we see here graphically. So 2.15 is going to be our second guess, and that's going to take our third guess, what appears to be just below 2. And so if I were to take now 2.153 and plug it into the same equation again, I now get 1.954. In just 3 guesses, the first one was a guess, the next 2 are iterations, I'm already within 1% error of the actual 0. So we can get very good results, depending on the function, very quickly with the Newton-Raphson method, and it's pretty easy to implement in code. Let's see how. If I were to take an anonymous function, and this is called an anonymous function in Matlab, it's denoted by the at symbol, so I would say f equals at, and then put in parentheses any of the arguments I want to pass to that function. What this does is it assigns f, instead of assigning a number, which is the way we deal with most things in Matlab, this gives that variable a function behavior. So now I'm going to say f of 0, for example, and it'll give me back whatever value is calculated by this second set of parentheses. So I'm saying f is a function of x. I could put x, y, z if it had 3 variables that I wanted to pass through it. And then this second set of parentheses denotes what that function actually is. From then on, I will type f of whatever argument I want, and it will give me back this calculation. So we're going to say f is x squared over 4 minus sine x, which is our original function, and then fp, which I'm just kind of shortening f prime. This is the derivative. I could say just as easily df is also a function of x, and that is x over 2 minus cosine of x. And so if we plot these two things, we get still the plot over here. I can check my function values by saying, okay, f of 1, that gives me negative 0.6 on my graph. If I come over here to x equals 1, then I can see, yeah, that's about negative 0.6 there. So that makes sense. Okay, so we're getting results that make sense. So we've got our function defined, we've got our derivative defined, and now I'm going to construct a loop in Matlab to loop this Newton-Raphson method. First, let's say what an acceptable error is. So let's say for a moment that error is 2 times 10 to the negative 5th, just to set the error bound. And we're going to take an initial guess, again, p equals 3, just so we can see this step through the iterations just like we saw in the previous slide. And let's go ahead and start a counter at 1. So I'm going to be counting the iterations so I can then also name them as I go through my loop. So to start our loop, we're going to get an initial value for the function and its derivative, and go ahead and plug in the second guess, and then we're going to start with our first guess or second guess and iterate. So our first guess is 3. I can already calculate that our second guess is going to be the initial guess, 3, minus f, which is this, of p of I, which is our first guess, over fp of p of I. And so I represents the ith element, represents the ith guess. So when I is 1, that's the first guess. When I is 2, that's the second guess. And so what we're going to do is initialize our while loop, because we're going to say while our change in guess is still bigger than a given error, then we're going to continue to iterate until our change is very small. So while the absolute value of guess I plus 1 minus the previous guess, I, is greater than our error value, then we're going to increase our counter and we're going to do the iteration again. And we're just going to continue this until we're not changing more than 2 times 10 to the negative fifth from one guess to the next. So that's all we're doing, is we're going to repeat the process that we did previously, and we're going to do it again and again and again until we detect almost no change, and then we're there. We've arrived at the zero. So we have done what's called convergence. We've converged to a solution. So the moment I type this into Matlab, it will run. The moment I type end and hit enter, it'll run that loop. And if you diverge, you'll know, because it'll just sit there and run and do nothing. And you won't get your cursor back, and Matlab will simply sit in there looping in its own mind for as long as you are willing to wait. So assuming we get convergence, it will converge generally very quickly. We're talking usually within 6 to 7 iterations for something like this. For more complicated algorithms or more complicated functions that are a little bit more difficult, sometimes it can take upwards of 100 to 1,000 iterations to get certain levels of accuracy. In this case, it should run in just a couple of milliseconds. You shouldn't even notice the computer think. And so if I type p prime, because it's storing all of these guess results in a vector p and making it longer and longer, if I type p prime, it should list them nicely in a vertical column. And so if I do that, here we are. 3, 2.1, 1.95, 1.93, 1.93, and here we see there's almost no difference, so we probably have a pretty good precision here out to 6 or 7 decimal places. The error here isn't necessarily just the last change in the decimal place. It's not as simple as that, but it's pretty close. So we have probably 5 or 6 decimal places of accuracy here in terms of where that x is. We can check then a little further and say, well, let's plug this last value in and see how close we are to 0, which may be of more interest than the actual x position. And so if we do that, we can take f of simply p of end, and that selects the last element of p in whatever direction that list is. So if I said end colon or end comma 1, then it would take the end of row 1. If I do that, then we get 5.5 times 10 to the negative 16th. So that's essentially 0. That's probably down near machine precision in this particular case. I'm not sure the computer could calculate 0 much better than that. So this is a pretty amazing approximation for what appears to be 6 iterations of this formula. So very, very, very fast convergence. And relatively stable, but you do have to know the derivative. So that's Newton's method in a nutshell, also known as the Newton-Raphson method, how to find a root with that. This method actually has a little bit more horsepower than previously indicated, however. Let's take a look at the original function again. Each new approximation for the 0 of a function is going to be equal to the previous guess minus a function divided by its derivative. Pretty simple. Let's say for a moment, let's move pi over to this side of the equation and say, okay, the difference between the next guess and this guess, we're going to call delta p. And that's equal to -1 times the function value over its derivative. Okay, pretty simple. So if we do that and then rearrange a little bit, then we have that the function derivative at the point pi times the change in our guess from guess I to guess I plus 1 is equal to the negative of the function value at pi. And this doesn't seem all that significant, except that I can arrange this in matrix form, and we recognize this as ax is equal to b. I know the derivative because I know pi, I know f prime, and I know f. And so this is known, all I don't know is delta p. And so I have a set of equations, in this case simply one equation, ax is equal to b. This would be a constant here for the derivative value because we're calculating that. We calculate this constant, and we can simply solve ax equal to b. And so we would get the b is, x is b over a, negative b over a. We recognize this as Gaussian elimination, a Gaussian elimination problem. Usually we teach Algebra 2 students, etc., to solve this using Cramer's rule, take a matrix inverse, for example, to solve a set of linear equations. And that's not necessarily good practice. in this case, we can do just a simple one-liner and do the algebra, and that's essentially what we did on the previous couple of slides, and that's solved already. However, this is useful if I want to solve more than one equation with more than one variable. Very powerful. And so we're going to do Gaussian elimination. In Matlab, we do that using the backslash operator. If I know A and I know B, I do A backslash B, and it gives me X. And so I can simply say that f prime backslash negative f of p is equal to delta p, and then assign the next guess, p of I plus 1, according to the known equation that we already have. So we can do that using this Gaussian elimination step. So to extend this to multiple equations, we realize that f prime is df by dx times delta p is negative f of p. Well, if I have more than one function and more than one variable, if I want to solve the two, I do need, without some optimization criterion, I need the same number of variables as functions. Not a problem. Okay, so in this case, let's say we have two functions, f1 and f2, and those are arranged by row, and we have two variables, x1 and x2, and in this particular matrix, we're going to arrange those by column. And so I'm going to take partial derivatives because this is a function of more than one variable. I'll take del f1 by del x1, del f1 by del x2. Again, function 1 is in the first row, function 2 is in the second row, variable 1 is in the first column, variable 2 is in the second column, etc., etc. You can do this for n functions in n variables. If I were to multiply that by an unknown matrix where I'm changing a guess in both x1 and x2, then that would be equal to negative f1, f2, this vector here. So essentially we have the exact same form that we had back here, ax equal to b, except I now have a matrix form that allows me to use more than one equation with more than one variable. This is called the Jacobian. This is a special matrix. It's used for a couple of different things. This is probably one of the more common uses for the Jacobian because we can use it to solve systems of equations that we can't analytically solve for the zero of. And so we're going to take these partial derivatives and we're going to take our original function and do Gaussian elimination on those, and each time we're going to update a set of guesses for multiple variables. So again, we're going to use the Gaussian elimination process to get those results. Let's look at an example. So what if we have more than one function? Let's take a look at an applications example. One common application of the Newton-Raphson method is to solve the position analysis of a kinematic mechanism. An example is the 4-bar. The 4-bar is one of the simplest mechanisms that we have. We can simplify it by saying, well, I know that these linkage lengths are constants. And so let's say there's a grounded link here that we don't see, and so I'm going to assemble links. Usually this would be called link 2, 3, 4, but in this case we're just going to say that this is link 1, this is link 2, and the other two links are known. And so if I know the position of these 2 points, so this point and this point, then what are angles x2 and x1? Can I solve for those? And we surely can. We can draw what are called the vector loop closure equations and come up with 2 equations, one that describes the equations in x and one that describes them in y. And so if we look at this from the perspective of f1 and f2, I can define x1 as this unknown and x2 as this unknown. I have one function of sines and one function of cosines. So I have c1 sine of x1 minus c2 sine of x2 plus some constant c3. Same thing in cosine. So let's give this some real values. These values do correspond actually to this roughly scaled drawing of a 4-bar, what would be a crank rocker. And so in this case we have C1 is 3, C2 is 1.75, C3 0.9, and C4 is negative 3.2. So if I write that equation out, then I've got these constants. I can go ahead and take the derivative of that as well. Happily, and this isn't exactly happenstance, it's the result of good planning, this function is differentiable easily. We can easily take the derivative. So remember, we're going to take the Jacobian. So I'm going to take del f1 by del f1, for example, for my Jacobian matrix. So del f1 by del x1 is simply c1 times the derivative of sine of x1, which is cosine of x1. And so if I take those values and construct the matrix that we had from the previous slide, here's my Jacobian, and as promised, here's c1 cosine of x1, which is del f1, this function, by del x1, so the partial derivative of f1 with respect to x1, c1 cosine of x1. So this is the Jacobian. These are unknown values. I'm going to take an initial guess at what x1 and x2 both are, and I'm going to set that equal to the functions as they're written here, and I'm going to iterate using the same Newton-Raphson method that we used for a single equation. So let's take a look at what that looks like for code. Let's say that C1, C2, C3, and C4 are set as we said. I'm going to take an initial guess, and it's going to be a little bit off, and that's okay. Let's say that my first guess for x1 is about 10 degrees and x2 is about 90 degrees. Pretty close. In this particular problem, this is important because you may have more than one set of roots. We do. In the case of a kinematic mechanism like this, you could assemble this in two different ways. So there are two real physical solutions for x1 and x2. So you need to make sure that your guess is close to the one of interest, because usually it's going to converge to the set of points that gives you the closest solution. So in this case, we're going to guess x1 is 10, x2 is 90, and we should come up with values that are relatively close to that. I'm going to start a counter I equals 1 just so I can watch how many iterations this takes. And I'm going to initiate my guess by, again, we're going to run this with a while loop. So I'm going to say, okay, del x at the beginning is just 1, just something bigger than what I'm going to accept for the error so that the loop starts. So in this case, remember that as I take guesses, I'm taking two guesses at once. And that's one of the things that makes this particular method a little bit stickier than the single function approach of the Newton-Raphson method, because each time we're changing two guesses, and we may have one guess start to go in one direction, one guess start to go in another direction, and if our functions aren't well conditioned, if our derivatives aren't behaving well, etc., we may not converge to where we expect to. So at any rate, we're going to take an initial guess of 1, 1, and this is of course a column vector, so hence the semicolon to put the 1 on top of the 1, because each time I'm going to get a column vector out of my Gaussian elimination. So we're going to say that as long as the maximum of the absolute value of del x, so it's going to take del x and both of these values, it's going to make both of them positive to take the absolute value, then I'm taking the maximum, and I'm going to say as long as that's bigger than 1 times 10 to the negative fourth, let's run this loop. And so because I gave it an initial value bigger than that, we will actually start the loop. We're going to say that A is equal to our Jacobian here. We're going to calculate that based on x1 and x2. So x of 1, x of 2. And so each time we're going to be overwriting the values in the x vector. And so I'm going to calculate A. I'm going to calculate B, which is negative 1 times the function value. So it's everything here on the right-hand side. And then I'm going to do A backslash B, and that's going to give me delta x1, delta x2. So del x is equal to A backslash B. Then I simply add that to my original x and run it again. So we'll say that x is x plus del x. I'm going to increase my counter, and the moment I type end and hit enter, it'll run the loop. This runs in just a few milliseconds on my computer here, and we see that x at the end, once it's run, I can type x and it'll give it back to me, and it says x is 16 degrees for x1 because this is the first row, and so x1 looks like about 15 degrees. That looks good. And x2 is 100.35 degrees, which looks good for x2. Makes sense. And so one thing that you can do, assuming this is converged, you can plug your values for x1 and x2 back into your equations and check them. In this case, and I don't show it on the screen here, in this case this took 484 iterations to reach that level of precision, and this isn't that precise of a result. We only went to 1 times 10 to the negative fourth. Because you're solving more than one function, it tends to converge slower. So you're going to be running a lot more iterations in this case than you would with a single function Newton-Raphson. It takes a little bit of subtlety and it takes a little bit of practice to know where to guess, etc. But you can play with a simple code like this and you can get multiple functions to go to 0. So this is one of many applications of the Newton-Raphson method. It's pretty easy to code. You just need to be careful about it. If you don't know the derivatives, then there will be another video on how to do this with the secant method. And so we can take any continuous function that maybe we can't differentiate, or not knowing the derivative is a problem, we can simply use a couple of points to approximate the derivative using a finite difference and get a pretty good result that way. And it's actually a little bit more stable in some cases.